Okay, guys, so we're going to talk about sequential circuits here. So far, we've been talking about combinational circuits. Combinational circuits are, I guess I think of them as circuits that don't have they can't remember a previous state. Anything at their output is some combination of their immediate state. Let's say a NAND gate, depending on what A and B are, the out is just going to depend on the present state of A and B, and not have anything to do with. Let's see, how does this go? That is low, high, high, high. So it doesn't matter what happened before. Okay, so NAND gates, NOR gates, inverters, etc. But that's not the only type of circuit we need for logic. Sequential circuits are, a very important part of the design. And they really what they do is they typically end up um, buffering or surrounding combinational circuits. So what you typically see is you'll see some combinational circuits and their inputs and outputs go to, say, flip-flops or latches that are being clocked. Okay, and then sequential circuits are circuits that where the output does depend on a previous input. For example, a good example of these is like, say, a finite state machine. So imagine a vending machine. So if all it knew, it didn't have any idea of a previous event, it would know that you put in coins, enough to pay for your Diet Coke. So imagine how a finite state machine works for a vending machine is it starts at, a waiting state, then, you feed it some amount of money, and that takes it to a new state where it's waiting for your selection of your drink, say, and then select your drink, and then it that takes it to another state where it's dispensing the drink, and then once it does that, it goes to another state where it's waiting again. So in each one of these cases, it has to remember what happened previously. And in other cases, pipeline circuits. So a lot of times in processors and lots of circuits where you want to create a situation where you can increase the throughput of your circuit. So let's say if you had a combinational logic that was very long and did some functionality, if you kept it as a long combinational circuit, you had your input and your output, you would have to wait this entire time, so T delay total, before the next, you have to, before your next, this is the total amount of time going through this combinational circuit, you'd have to wait that entire amount of time before you fed in the next input. Whereas with a pipeline stage, let's say you divided this into two halves, so each one of these elements in the pipeline had a T dt, T delay T over 2. That means you could keep feeding data into here, and then once the data left this pipe and went into the second half, you'd be free to put your next batch of data in here. So immediately you can, you've essentially increased your throughput by a factor of 2, or is it a factor? Yeah, I guess it'd be a factor of 2, maybe something like that, where you can keep feeding this thing data at a rate of TDT over 2. You'd still, the total latency from the input coming into here to the output going there would still be this TD over 2, but you can fill this pipeline with more data and you can get more throughput. Okay, so those are all examples of things that require elements that can distinguish between what happened previously and what will happen next, etc. Okay, so now these circuits, the things to think about, one of the main aspects of sequential circuit design is that there's clock going into flip-flops, clock going to latches, to have an idea of time for a circuit. Since it doesn't grow old like us or it doesn't have a watch, it needs some kind of a pulsed clock that's telling it what happened in this clock cycle compared to the previous one. So basically we have a situation where we have, think about your chip, and you have a clock that needs to get distributed to all points or a lot of points in your circuit. And again, you have, billions of transistors and probably millions of flip-flops or latches or, sequential circuit that need that clock. That's going to be, this clock is always the most loaded from a capacitance standpoint node in your circuit. So when you look at the power consumption, the clock going to these sequential circuits is, the power consumption, if you remember, is alpha CV squared F. So the capacitance, the clock has huge capacitive load. It's going to all these sequential circuits. It's running at the highest, obviously the highest frequency in your circuit by definition. And it's by definition chugging along in every cycle, so its activity factor is also 1. So, if you look at the clock in your circuit, it might be taken up, 25% or more of the IC's power is, taken by the clock. It's a typical number, but it's not unusual. Okay, so that's one thing, is the amount of power consumption that the clock circuit will take. The second thing that you have to worry about, which is unusual, is a concept called skew. You hear this a lot when you are talking about combinational circuit. And the skew is the delay between the actual clock and, you have this sort of theoretical clock that's all supposed to be the same, happening at the same rising, same falling edge. But in reality, if you build your clock network, say you got a bunch of buffers here, so at some points there is a small delay going to some points, and there might be a much bigger delay if something's farther away from the source where you generated your clock. So the difference between these these delays is called the clock skew. And depending on how you distribute your clock, you have to be careful that that the results. So this is going to a clock at point A. This is going to clock at point B. So let's say this is, clock at point A. So there's a bunch of delay here. This is clock at point B, at point B. And so you got to be really careful that you consider the fact that these these two layers are not getting the clock at exactly the right time. So you have to make sure you account for this potential delay between the real clocks going to these nodes. And that's this difference is called the skew. Okay, so let's see. We talked about pipelines, pipelining and circuits, important and sequential um, circuits. Now, so these are really, for having pipeline stages, for having finite state machines. These sequential circuits are great, but there is inevitably a some overhead, and this is there is some amount of added delay. So if you had, again, in the case we took this combinational circuit that had a total delay, and we divided it into two blocks with half a delay so we could get more pipelining in. But to be able to do that, we had to add flip-flops. And each one of these flip-flops has its own delay. It has its own timing requirements. It's not just a delay, but we'll see it has its own timing requirements. So this, some people call this the clocking overhead. It's basically it's an effect of basically creating the sequence timing in sequence. You have to insert these additional sequencing elements, and there's just a natural overhead associated with them. So we'll look at how you can analyze that and what it might be. And again, it's a very important factor about the limitations, about the maximum and minimum delays that you can achieve or can allow in these combinational circuits. Okay, so the first thing is, I don't know how much experience you guys have had in your logic design classes, or maybe you've done this Verilog, etc. And there's two kind of sequencing elements. There's latches and there are flip-flops. Latches are level sensitive, meaning that if the clock level is depending on, let's say that the latch is clock high level sensitive, that means any input that happens during the high level clock shows up at the output and gets stored there when the clock is low. In a flip-flop, everything happens on an edge. It's triggered on an edge. So let's take a look at it. I think it's just easier to look at it here. So let's say you have a clock going to your latch and your flip-flop, and you have the same input D going to both circuits. Now let's look at what happens at the latch and the flip-flop. So here's the latch output. So what happens at the latch is anything that happens during the rising edge goes to the output. So here, with some delay. So here the latch will, the clock is high here, all here. So the latch output will just follow the input. And the latch, when the clock is low, then the latch doesn't follow the input. It'll just keep the stored value that it had the last time the clock was high. So if the last time the clock was high, the latch output was low, then it'll stay that way. And it doesn't matter if whatever D does on the input, and it'll just stay that way until clock goes high again, and then the latch will start following the input D. Okay, flip-flop is only works on the rising edges. So let's say initially, for the sake of discussion, let's say just to make it clear, let's say initially the value of the output of the flip-flop was high. So as soon as it would stay high until the rising edge of the clock happens, and then since the D is a low value, it would go low. And all through here, it wouldn't matter what D is doing until you get the next edge of the clock. So it would stay low here, here. It wouldn't care what D is doing. Here, it wouldn't care what it's doing. It would just look at this edge and see, okay, D went high over there or is high, and then its output would go high. So that's the difference between those things, between flip-flops are edge triggered and latches are level triggered. And as we'll see, those will cause some significant difference about how you use those two. Okay, so here's sort of a history of latch design, and the reason we're going through these is just to okay, sorry guys, that was an interruption. The reason we're going through the sort of the historic performance of these latches is to give you an idea about why we have the latches or flip-flops the way they are now. So this is when, when transistors were really precious back in the 70s. This is where everything started in the form of a latch. And it's really just a pass, looks like a pass transistor. And there's a capacitance that naturally happens. You can think of it as the drain or source capacitance of the output. And you can basically store the value there. So it's like you're just dumping the signal here, and you're storing the value there, and the value will stay there for a while. And then because of leakage and etc., it'll start drifting down. So let's see what it would look like. So let's say here's the clock, or be, clock is sometimes referred to as phi, so clock. And let's say it's doing this. And let's say the latch is the data input D does something like that. And let's say initially the latch output Q, and say it was initially low. I'm gonna have to put, well, let me see. Initially it was low, and then when clock goes high, it'll go to the VDD value, but it won't go all the way to VDD. So you have to remember that since we have an NMOS, if the input is high, so if the input's at VDD, the output is only going to go to VDD minus VT. So this is the first problem that it has. There's a threshold voltage drop from input to output when D is high. Okay, so that's one. Two, there's nothing, so basically you don't get a full and clean one value here. It's kind of a cheesy, or it's not a great one. So I would say it's non-restoring. There's nothing at the output that will clean up this VDD minus VT and increases the size. And the output when the latch goes down, there is charge here, this channel charge here, negative charge. Some of it will go back to the input, but some of it will get dumped here as you turn this device off. So actually you get a further reduction you'll get this sort of lower going pedestal here because of the so-called charge feed through. We haven't really talked about this, but it happens in analog circuits quite a bit, and here too. And then finally, if it's sitting there long enough, you have leakage current, etc., on that capacitor, and it might be a pretty low capacitance value if you want to save area. So that value will start even going down further, leaking further as time, with increasing time. So you'd call this, a dynamic latch. Dynamic data is only good for a certain amount of time. Data needs to be refreshed. The other thing is it's also very sensitive to crosstalk. If you guys remember the section on uh, we just talked about wiring and interconnects, and we said when you're talking about the worst case crosstalk is when a node is floating. It's really, really sensitive to neighboring circuits. And once this data is being stored here, it's just sitting there floating. So it's very sensitive to noise. Let's see, what else do I want to say? There's a few other things, is that you got to be careful when you're driving. No, you're no longer driving a gate. Remember when we were driving, it's always a much more known situation when you're driving the gate of another device, because you're pretty much guaranteed that nothing funky is going to happen. This is just purely a capacitive load. Here, it is possible that you have overshoot or undershoot, as you guys remember, like your voltages input don't necessarily, so whether it's going up, it's not necessarily going to look absolutely clean. Um, as you're seeing in project 3 or in the projects that you're doing, that you get glitches and all that stuff. And going to the source, driving a diffusion, if those are big enough, they can start causing some problems. So you have to be worried about that. And lastly, if you have, let's say you've got, um, let's see, what could be the case would be if there's another possibility that there's another latch here going the same output, you're hoping to cut it off, but it isn't. It's possible for something else to drive this input the other way. So it could have something fighting with your driving circuit. So that's called back driving, which is also a potential problem. Okay, so the next step, so these are all the issues that we had with the simple pass transistor. The next step was to go to a transmission gate, which we're familiar with. This was the case where we have no VT drop because we use both an NMOS and a PMOS in parallel. So a high value would go through the PMOS and you'd have the full value. But again, you'd have the problem that this is just sitting in a capacitive node and it's drooping, and it would have all the other issues. But the one nice thing is at least you don't have the VT drop. You would get a full high level signal, a full one here. So that's nice. That's an improvement over the previous circuit. Now the downside of this compared to the previous circuit is you need not only the clock, you need the inversion of the clock. So if you had, if I was going to design it simple, or look at it simply, you would need this extra inverter to invert the clock. So, or you need both the clock and its inversion. Okay, so that's the downside of that latch. The next thing people started doing, and notice all these are also causing extra power consumption because we are driving more capacitance with our clock, and we're adding more, so here's even the same, more capacitance, and we're adding more transistors. So here you have a situation, let's say if you have an inverter at the output, you have the added benefit that this is restoring, meaning that it's really giving you, if you're sitting here at a sort of a 1, you'll get a real 0 here. The next inverter will clean up the logic level to some extent. So it's a restoring level, and there's, if something's trying to drive this inverter will stop it, so there's no back driving. Or you basically are driving, depending on where you put the inverter before, after. If you put the inverter before, whatever's driving this latch won't see this diffusion. So as long as you design this or whoever designed this latch properly, um, you won't have to worry about this sort of glitch in a source drain. So that's good. Now, one negative side is that the output is inverted compared to the input. So before we had D and Q, now we have D and Q bar. Okay. The next step was, so all these things so far are still dynamic latches. You're storing this value in some capacitance out here. Then the next step was to create a static latch, and the idea was to create a so-called back-to-back inverter stage. So imagine if D was high for a second, if D was a 1, the output at Q bar would be 0. And then this inverter here would take that 0 and emphasize the 1 at the input of the X. So this is a positive feedback circuit. So when the clock goes low, this guy gets enabled, and you cut off the input, and then this positive feedback circuit keeps this value at X and keeps Q bar, so you won't get leakage. So you'll get a static circuit. Now, one dangerous thing about this is you could, if your timing isn't great here, there's some, let's say your delays are a little messed up between this transmission gate and this inverter enable, you could get a situation where D and the output of this inverter are both fighting for X. So there's a backdriving risk. So anyway, now basically, I think it's very rare that you see dynamic latches. So all the latches now are essentially static, just because the leakage currents at these advanced nodes are way too high to just let nodes floating. So having a feedback is essential. And then people basically, that's kind of the main thing. Now you're just adding niceties here again. So the main thing is you have this positive feedback stages. Now you can add an inverter to drive the input easily and have it be, a non-inverting output, so non-inverting diffusion, no, not driving diffusion. So, and essentially that's kind of all the latches you see now are very much like this basically. So, and and people, you can keep adding inverters, etc. So you can separate your actual output Q from your feedback circuit, etc. And this ends up being solving a lot of your problems, but it does have some issues compared to where we started with. So it's robust in the sense that you don't have to worry about leakage, um, no backdriving. It's more sensitive or less sensitive to crosstalk, etc. But compared to where we started off with one transistor. Now we have two, four, six, eight, 10 transistors in compared to just one transistor for where we started, not to mention the clock and clock bar requirements. So it could be pretty large. It's got, a certain amount of delay because this inverter is driving a bunch of stuff to begin with. And then the clock is driving two NMOS gates, and the clock bar, which is part of the clock network, is also driving two gates. So it's got a significant amount of clock loading. Okay, so people have sort of maybe sometimes they back off of that for data paths, etc. But you guys get the idea. Latches are sort of variations on this thing now. When you have a static latch, you always have a positive feedback circuit. You have something that controls when the positive feedback controls the storage node, and when the input controls the storage node, and you may or may not have some kind of a buffer. Okay, so it turns out that flip-flops. So this gets quite a bit more complicated than um, a latch. Really looks like sort of two latches back to back. And this functionality creates a something that's edge triggered. And it's always had a hard time trying to figure out why edge triggering is important. Well, hopefully it'll become more clear when we start talking about actual clocking. But let's just keep going talking about it. So one thing is that flip-flops also can be either dynamic or static. And the difference being that the static has the positive feedback latch and the dynamic has the dynamic latch. So let's talk about the uh, the the static case. So this is latch 1. This is latch 2. So let me just start by drawing the clock. Phi. And phi bar. Whoops, phi bar. Which is just a clock inverted. Okay, and let's have some D input. I'm going to make something up to hopefully it'll show us some interesting cases. What do I want to do? I want to put it here. that good? Okay, that's what I have. And then let's look at what happens in node X, which is here, and Q bar, which is obviously here. Okay, so let's first look at X. Okay, so X initially here, when the clock is high, so when the clock is high, X is cut off from the input. Okay, notice the clock phi is going to PMOS. So when the clock is high, so the X is just sort of storing what it was there before. It's not moving. Okay, so it's just, I don't know, it's going to this intermediate stage or this point. Let's say it started off with a 0. And then when phi goes, the clock goes low, in this case, the clock goes low, both of these guys turn on, and then X starts following D in this case. So it'll go up here, and it'll go down, and it'll go up here. And as soon as the clock goes high again, X will just keep its value. So it doesn't matter if D, so let me change D here to show that even if D changed in value after that, it doesn't matter because here and here, so for these, X is cut off from the input. Okay, and then let's look at Q bar. So Q bar, when the phi is high, okay, when the clock is high, Q bar is just going to be the inverted version. See, it's one inversion, two inversion. It would be an inversion version of X. So X is doing whatever it's doing while phi is high. Okay. And then when phi goes low, phi is cut off from X, so you won't see anything from X. It's Q bar. So it won't, all this stuff that's changing with X doesn't affect Q bar. And then finally, when phi goes high again, then you get Q bar following X, inverted version of X, and then it basically changes. Okay, so basically what happened here is we have only during an edge, a rising edge, does sort of the whatever value D had affect what happens at the output. Okay, so it sort of ends into an triggered or triggered sequential circuit. And that's because you have two back-to-back latches. Okay, and so that's how a flip-flop works. It's a little, it can get a little complicated. You might want to sort of try to follow this yourself with various inputs and see how it works. But the main thing is latch is level triggered and flip-flops are edge triggered. And then, you can go through a lot of these variations in flip-flops. Enables are very important in flip-flops. You don't want them to always work. And resets are absolutely important to flip-flops. If this is another one of those things that if you don't ever remember anything about this class, except for this, it might save your life someday, is make sure that you can reset all your latches. So there are non-resettable latches available to libraries, whether you're talking about FPGAs or or um, or ASICs or custom designs. But if you don't have a reset on a latch, imagine if when your circuit powers up, these latches or flip-flops could be at any state. So you may be in a situation where the circuit is completely non-responsive to outside stuff completely, and no amount of input is going to be able to change that. And if you do not have a synchronous reset, so important, even your clock may be off because of, that your chip's not working properly. So I think it's very important to have um, reset. Okay, and I would suggest strongly to make it asynchronous because synchronous reset is relying on your clock circuit working okay. And the fact that your flip-flops are coming up in an unknown state may mean that um, your um, your clock circuit itself isn't really working well when you power up. So anyway, it's really, really important in my opinion to have one, I think reset on all your flip-flops. I really argue that's critical, and then have it asynchronous, which I think is important to make sure you have control over the startup state of your circuits. Okay, guys, so I'll stop there, and then next lecture, which will be our last one, we'll be talking about the actual sort of sequencing methods and clocking.